Good afternoon. In the previous lecture, we talked about how do we use machine learning to perform denial of service attack detection. Now, we are going to look at how do we try to find or detect another attack like eavesdropping attack. And as you will realize, although the attack is different, the whole machine learning story is pretty identical. So, what is eavesdropping attack again? In eavesdropping attack, a sender sending a packet to a destination D, and in between another attacker is sitting, and attacker is able to kind of sniff or get the packet. That is basically the idea. So, that is the eavesdropping. So, you want to figure out whether the eavesdropping going on. Now, if the attacker is sniffing only 1 or 2 packets, it is very difficult to figure out for anybody. But if it is sniffing a lot of packets in a certain time, then by looking at the traffic in certain kind of area, you might be able to make a thing. So, there are different kind of detection and analysis technique, but the key idea is the existing ones are for very highly predictable scenarios. So, machine learning will be able to kind of consider variations, and this story is kind of same thing. So, you kind of have a attacker somewhere that is trying to do an attack or listen to somebody, and it could be implemented through some form of Trojan and some node, and then it kind of work together. Now, it is not just that it can copy packets. So, copying is basically the payload here for the Trojan, but after it copy it sends it to somebody another node. So, think about it is copying it here, and then it might give it to the another node where a program is running, and they together collaboratively kind of may do the attack. So, as you will see, the kind of whole idea is you want to do feature engineering of the NoC traffic, then you want to collect kind of the data, and so during this kind of training time you kind of have those kind of stories. So, model they do the training, and then you have those training done, then during runtime you still do data collection during runtime, and wherever you are making the decision, wherever you installed your machine learning unit, and then you kind of infer is it a eavesdropping attack going on or not. So, here is the detailed algorithm eavesdropping sensing, but key idea basically is that when you kind of look at somebody trying to communicate from 1 to so from 0 to basically 15, at that point the attacker in the middle is kind of sitting here listening and then trying to kind of send to different nodes for kind of processing. And this diagram that you have seen, it may look exactly the same, because it is doing exactly same thing. You collect the log or the traffic traces in the NoC, do kind of different type of feature generation, then you kind of figure out redundant feature you remove, initial model training, then you do model validation, choose which features are good, then finally you kind of do the testing to figure out do I have a model that is going to work. And as I said, there are other features that you might want to use, whether in terms of path, position and all that might be useful. This all of this we kind of have looked at. So, in terms of results, how well does it work, that depends on how much of eavesdropper, how much of data the eavesdropping is going to consume. We still have similar kind of configuration that in a normal in node 0 and node 15, normal one is working on, and attack is going on node 2 and node 14, right. So, for example, node 2 here and node 14 here, they collectively work together. So, they are working, and as you can see the train configurations, whatever attack, and the test configurations, they have no similarity, they are totally different. And in terms of the different performance kind of, if you look at for the regression, multi-layer perceptron, decision tree, random forest, as you will see even the previous one XGBoost was kind of doing better, this is also doing better in this particular case. And this particular was when 50% of the data is sniffed by the eavesdropper. If eavesdropper is, and this prediction accuracy, no matter which model you take, let me see if I have the result. Yes, I do. So, basically when you have the amount of data that is getting sniffed, if you look at when you have kind of, this is the training one, right. So, when you have about 50% data, you are looking at somewhere around 85% validation. When somebody is sniffing 100% of the data, even then you are looking at somewhere less than 95%. But if you consider 25 or 10% of the data, then your prediction accuracy is low, very close to random guess. So, less and less data the eavesdropper consumes using a standard machine learning techniques like this would not work. So, if you want to publish a paper in this area, what you have to establish that you can build a model, machine learning model, that is going to consume 10% of the eavesdropping scenario, and it can still do a wonderful prediction, not 60%, maybe 70-80%. If you just get those results, that is not publishable. You have to have an intuition why machine learning or which type of machine learning model, how did it figure out with such a little data. Because what it's figuring out is, remember, extra traffic, extra conjunction, extra pattern manually when we are doing, I wanted to show you, that is what machine learning tool is trying to figure out. It is trying to figure out the normal pattern versus abnormal pattern, that is what it is. Any questions? So, for different kind of then the scenario and different traffic kind of story, as you will see the accuracy kind of the EC1, EC2, EC3 different scenarios, it depend on the scenario, but you are looking at kind of different kind of number in the accuracy. That is pretty much what we normally care. We also should care about these numbers, and these numbers are not small either. False positive is actually pretty deadly, false negative is different, but false positive is pretty deadly. You are basically saying the attack is going on, but when it is actually not going on, and that is 23, 19 or 2% of the time. So, now that we kind of talked about different types of attacks and your detection in machine learning, the last one I want to talk about how do you use machine learning to make attack on the NoC itself. This time machine learning is the adversary, earlier machine learning is the friend who is going to tell you something going wrong. So, I want to show you examples of two scenarios, but there are many such scenarios we can discuss. First scenario is traffic analysis attack, second one is breaking anonymity. So, if you recall, we kind of talked about different type of fabric, one is electrical fabric, another is optical fabric, and then we also talked about this kind of wireless fabric, right. So, in case of this wireless fabric, each node is, so this is a 4 cross 4 16 configurations, each of them has a wireless router, and the assumption is anybody wants to talk to anybody, it is a one hop connection. So, if you are thinking in electrical terms, it is point to point communication, as if everybody is kind of. So, if I wanted to create instead of 16 cross 16, if I want to create a 2 cross 2, it would be connection like this in an electrical domain. Anybody you can reach with one hop, and because everybody has communicating tower, so they would be able to talk to each other, right. So, in this particular example, we call these as wireless hub, and this is the one which is transmitting right now, and this is the malicious one which will try to do whatever it is. And so, what you are looking at here is then this wireless kind of communication, you have time division multiple access based medium. So, this is also called MAC, but it is not message authentication code. This is basically medium access protocol, medium access control that is used for doing this communication, and this is very common known as TMAC, TDMA MAC, that is basically kind of used for wireless communication. And for this wireless NoC, what you are seeing a timestamp, this is timestamp 0, or think of clock cycle 1, this is clock cycle 2 picture, this is clock cycle 15 picture, and different people are, the story is different people are talking at different time. And remember, this is time division multiplexing. If everybody starts talking, assuming the RF bandwidth is for one person to talk, then everybody starts talking or multiple people start talking at the same time, then it is going to be serious interference problem in wireless communication. So, therefore, similar to the story of if you have a bus, similar to the story of if you have a processor 1 talking to processor 2, and if the bus is 32 bit, two people cannot put the request the 32 bit instruction, 32 bit data at the same time. Two people cannot do that, only one can do at a time, because if two people try doing it, somebody wrote 0, somebody wrote 5, you do not know what value will come out of it. It does not have to be even 32 bit, it can be just 1 bit line. If one person is writing 0, another person is writing 1, and you ask what is the result in that, it is non deterministic. In hardware community, you call it tri-state. But whatever it is, that basically means these two people, the bus will not allow these two people to write at the same time based on bus arbitration or whatever protocol. Similarly, in wireless community, this TDMA kind of protocol, that basically, so TDMA kind of protocol would basically block you from communicating at that time, whether they selected based on priority or other, that is beyond the discussion at this point. But it is clear that you are looking at, you are taking a camera and looking at a snapshot what is happening here. But what is important here is the malicious router can kind of snip at every time slot. Whoever is talking does not matter, they can snip and listen, because it is all one hop, and that information is in the air. The idea of one hop is when this person is broadcasting, technically anybody can hear, anybody can hear. Now, in reality, that the story that you have seen here, this is kind of theoretical. It is the designing, implementing, making sure there is no interference when they are sitting so close in millimeter square range. You are putting 16 antenna, just 2 millimeter or 4 millimeter square range. That's not kind of effective. So, then most of the time storage would be similar to this, which is you will have full electrical connectivity, at the same time you will have few towers. So, therefore, if you are trying to communicate from some point to some point, let us mark this the first one as, we can randomly choose this one as a source, and maybe we make this one as destination. Then there are multiple ways. So, probably the closest way would be to kind of going from here to here one hop, then use this wireless connection to here and then to here. There are other possibilities, but this is probably the shortest one, right. So, that is the communication in a hybrid one. Oh, so one thing I forgot to tell you is that here the TMAC token is circulated in round robin manner. Which one would get the chance to pass the data, because this person might say please send mine. So, everybody will kind of might have some request pending, but who will get the chance in this one, it is basically round robin manner. Right now this one has token, so this will transmit, maybe next time later based on the protocol, here is a circular, next time step this one will circulate, this particular token will come here, next time step it will come here, next time step it will come here, and then it will just rotate. So, that is basically the protocol, time division multiplexing protocol for just 4 wireless hubs. And because of that, it should be obvious to you if I just plot it. So, this one is for first Fourier transform, these are again real benchmark from splash benchmark, and this one is FMM, 2 benchmarks. And if you look at it, whether and these are there are 2 hubs, no 4 wireless hubs, and 2 of the benchmarks running, and if you look at it, if you kind of draw a vertical line, you will kind of figure out they are not kind of crossing each other, it is just different kind of time step. When they are communicating, they are kind of communicating in kind of different time steps. So, based on the token and what not, and ideally even this one is not supposed to align with this. This line also not supposed to align with this, even for second benchmark if they are running simultaneously. If not, then it does not matter, but this is basically time slot occupancy, how whenever a wireless hub is getting chance to communicate the data with another wireless one. So, basically TDMA you are looking at. So, like in normal world, non wireless world, when you have a program, the kind of characteristics you look at different programs are different. Similarly, in this wireless communication world or network on chip network world, when you look at data packet and control packet. So, data packet is the data values. So, when you have a packet, right. So, if you wrote an email that got divided into multiple parts, and each of the part is taken into a packet, that would have header and MAC and actual data in the message itself and so on and so forth, and whether this arrived or whether this is second one, request, acknowledgement, all of that. So, when message is involved, those are called as data packet. When any of the information of retry, if you are retrying, if it did not come in, or the acknowledgement or any other stuff, that is known as control packet. Ideally control packets are smaller, data packets are larger, but for the simplicity of implementation, most academicians make them same size, but whichever way it is, if you look at different benchmark, the amount of control packet data packets are different, right. So, closest analogy in programming language would be you have data path and finite state machine, or you have number of if statement or for statement versus regular assignment statements. So, this is similar to in terms of packet, there are typically more control packets than data packets. So, what is the threat model in this particular kind of scenario? So, basically the threat model goes like this, that you have this 4 cross 4 kind of story, and then you have multiple one, and one of the maybe this wireless hub has the capability of kind of in that their protocol TDMA MAC protocol, there are some kind of Trojan or some kind of malicious implant, and what they are able to do, they are able to sniff the data and then send it to an outside node. It could have been one of the inside node, where it has kind of some neural network to do some kind of analysis. So, this is typically known as colluding application. Now, it is quite possible that application also sitting in that same node, it does not have to be in another node, but it could be in another node, another place. Remember, it has a wireless the communication capability. So, it has much better leverage or power, attack power than somebody with electrical connectivity. So, in detail how does it work? Basically then you have some Trojan or malicious implant that is extracting some of the information and then extract the TMAC traffic trace. So, from the traces, then it kind of based on certain observation what something is happening or a trigger condition, it is going to activate the HT and pre-process and combine traffic traces and then deactivate the HT, because if it keeps itself activated, everybody else is listening. So, they might be able to figure out. So, then get the traces and then kind of send the traces to another adversarial node who will basically infer it, and the wherever you are sending, if you are an attacker, you already pre-trained the model for your attack and then you are basically making use of it. So, how well does it work, how much it is able to attack, or so what it is basically in this particular example, what is trying to figure out is what program is running there, right. So, what program is running there, that is what it is trying to figure out, or who is talking to whom, whatever it is trying to figure out, the basically accuracy is pretty kind of high with 2 layer CNN, and if you go for 4 layer CNN, now this CNN neural network is the attacker's neural network, not yours or mine. So, this basically the accuracy is very high. With high accuracy you can figure out what is going on in the victim node with reasonably high accuracy. Even with a 4 layer CNN you can get close to for certain topologies. I believe one of them is mesh, another is Toro and all that. So, certain topologies, it is even with 100% accuracy you can figure out what is going on. So, this attack is very kind of powerful, and there are certain defenses also. I am going to skip those. So, now I am going to talk about the last attack, which is actually simple to explain and which is called flow correlation attack. So, the key idea is when two people are talking, and even if it is kind of encrypted data, how do you figure out who is talking to whom, right. And so, because whenever there are kind of the idea of many of the time people kind of do this what is it called you kind of do onion routing, right. We talked about you do onion routing and anonymous routing, and many of time in the computer networks the idea is all of these, the whole network itself is anonymous, anonymity is preserved here, but anonymity is not preserved at the source and at the destination. So, if it is not preserved, then somebody might be able to do somebody might be able to figure out by looking at what is going on here. If this is, think about this is unencrypted and this is unencrypted, then you can figure out. Of course, how they will talk, that is different, and in fact, any of the network like Tor network, that is completely anonym, gives you guarantee of anonymity. But when the communication enters the Tor network or when it exists the Tor network, if two computer can sit there and analyze the traffic pattern, assuming other people are not talking at that time, then it will be able to figure out who is talking to whom, because everybody's talking pattern is different. How frequently I call Professor Sahu, if somebody is observing that kind of number or pattern, then you know who is talking to whom. So, that is basically the key idea here. And the way basically attack happens, that you do training time, you kind of do the data collection, you train the attacker DNN, and then here during attacking time you are basically potentially communicating pair, you are coming and predicting correlation, and you are basically breaking the anonymity. So, if you are thinking from a machine learning perspective, during training time machine learning kind of figured out all these combinations. It figured out if R1 is talking to R11, how the pattern would be, if R1 is talking to R9, how the pattern would be, R5 is talking to R15, what the pattern would be. So, it kind of figured out. Now, when R1 talking to R15, it really does not say much, what R1 is running, that is important. There is also something important, because the thing is, when remember the number of control packet, data packet that I have shown, how much and how many, and the frequency. If you recall, we talked about for loops and cache accesses, cache misses. Depending on the computation or depending on the messages, the frequency, interpacket delay, all of that has important correlation, right. And if every day you call your mother at the morning or evening, if there is a call coming to your mother, then neighbors will know it is coming from you. Assumption is nobody else calls you that time, right. So, whether it is the time of arrival or whether the frequency of arrival, that uniquely identifies everybody's unique characteristics. If everybody decides to call their mother at random time, of course, neighbor will not be able to figure out, and in fact, that is one of the mitigation here. Any question? Is the key idea clear, that even if you make completely wrap this with a secure envelope, secure entourage, if somebody has a listener here, somebody has a listener here, and all they are observing kind of the pattern of arrival, pattern of call, think about it, pattern of messages and their distance between them, frequency arrival, how many coming within what duration, and somebody is observing here and they talk to each other, then it is completely broken. Anything in between completely secure. So, these are all secure channel, like you can think of virtual private network or any other mechanism. So, the key idea is I kind of trying to pictorially illustrate. So, interfleet delay. So, what are these fleets? Think of packets or smaller fragment of the packet and what kind of delay it kind of demonstrate. So, once you have that kind of information, you just basically match whether this information here is actually same as here. In this picture I intentionally interfleet delay at the source, and this I basically just photocopied. Interfleet delay at destination is same, then you kind of know that is what it is, and effectively the attacker is trying to do the same thing wherever it is sitting, the based on that. But this is assumption basically relies on the fact during training time the attacker is able to know who is talking and what frequency they are, what application running, how their pattern is, and the machine learning model is trained. And if you look at the kind of results, then you will see that for different kind of mesh sizes, whether 4 cross 4, 8 cross 8, 16 cross 16, you will see the accuracy is reasonably high using the idea of interfleet delay or flow correlation attack. Any questions? If you have no questions, that is where we end today. We will see all of you tomorrow at 10 o'clock. Thank you.